Okay, let's try to solve a linear system with the breakpoint. So consider the following system, the following linear system: 2x1 plus 3x2 plus x3 minus b1 equal to 0. Second equation is 4x1 plus 6x2 plus 2x3 minus b2 equal to 0. Finally, we have the third equation, x1 plus 3x3 minus b3 equal to 0. This is a system. In our system, we want to determine x1, x2, x3, because in our economic system or physical system, x1, x2, x3 are endogenous variables, so are determined inside the model. b1, b2, and b3 are exogenous variables, so are given in the model. In order to solve this system, we can write the system in the following way: 2x1 plus 3x2 plus x3 equal to b1, because we put this first exogenous variable on the right hand side. Then we have 4x1 plus 6x2 plus 2x3 equal to b2. The third equation is x1 plus 0x2, because in the third equation we can't see x2, so the coefficient will be equal to 0, plus 3x3 equal to b3. This form the system, because we want to solve this system, this economic system, can be written in a matrix form. If we consider matrix A defined as a matrix of coefficient of endogenous variables, this can be written as 2, 3, 1, 4, 6, 2, 1, 0, 3, the coefficient in each equation of x1, x2, x3. Then we have the vector x defined as the vector or the column vector of endogenous variable x1, x2, and x3. Finally, we consider the vector b of exogenous variables b1, b2, and b3. Now, applying the product between two matrices, we can write this system in a compact form as ax equal to b. Matrix A multiplied by vector x equal to the vector b. We will see that the vector x can be derived computing the inverse of matrix A and multiplied by the vector b of exogenous variables. We will define the inverse of matrix A. If this matrix exists, we can compute each exogenous variable, endogenous variable, in terms of all the other exogenous variables. We can also consider comparative statics problem. Now, in this particular system, we can see that the second row is given by the first row multiplied by 2. So, what we can say that in this case the determinant of matrix A will be equal to 0, because rows are not linear independent. When we have two rows or two columns that are not linear independent, the determinant of matrix A will be equal to 0. When the determinant of matrix A is equal to 0, the inverse of matrix A does not exist, and we will see why. And so in this case, the system we are trying to solve has infinite solution or no solution. In order to understand, let's consider a simple, very simple system of two equations of two variables, x1 plus x2 equal to 1, x1 plus x2 equal to minus 1. We know that this system has no solution because there are no values for x1 and x2 which satisfy these two equations together. So if we we write the matrix of coefficient, this matrix is the matrix 1, 1, 1, 1 for endogenous variable, and the determinant of A is equal to 0. So in this case, why the determinant of A is equal to 0? Because the first and the second row in the matrix of coefficient are equal. So it's obvious that it's trivial that the first the determinant will be equal to 0. In this case, the system has no solution. If we consider the same system, x1 plus x2 equal to 1, and we repeat this equation, x1 plus x2 equal to 1, also in this case the determinant matrix of coefficient will be equal to 0, but in this case the system is not impossible, it's not as infinite solution, because we have the same equation two times. The same if we have the first equation x1 plus x2 equal to 1, and the second equation is equal, for instance, 2 times the first equation, so 2x1 plus 2x2 equal to 2. In this case, again, the determinant of coefficient matrix will be equal to 0, because the coefficient matrix will be equal to 1, 1, 2, 2, so the determinant of A applying the rule will be equal to 0. And the system will have infinite solution, because the second equation is equal to 2 times the first equation. At this stage, it's better to understand the intuition than this consideration. In this first system, the second equation is not given by the first equation, but by the first equation, because this part is different from this part. So in this case, the system has no solution. Now, if we assume that the determinant of matrix A, so matrix of coefficient, is other than 0, we can compute the inverse of matrix. In order to, if we have a matrix A, we can consider as first the matrix of cofactors. We know if we have a square matrix, we can consider a matrix of cofactors C11, C12, C1n, and the last row will be Cn1, Cn2, until Cnn. Then we define the adjoint matrix A plus as the matrix of cofactor. We can call this matrix C, and the adjoint matrix is the matrix of the transpose of the matrix of cofactor. So the inverse of matrix A can be computed as 1 divided by the determinant of A times the adjoint matrix. And now we are going to see a very simple example in order to understand this procedure. Okay, let's just start to consider 2 by 2 matrix A equal to 1, 2, 0, 1. First, we need to consider a matrix of cofactor C. We have the cofactor of the first element is equal to, in this case, the element we get deleting row and column of the first elements, but we need to consider the sign. So minus 1 to the power of the position of this element, which is 1, 1, so minus 1 to the power of 2 is equal to 1, multiplied by the determinant we get deleting the first row and the first column, we get 1. Then we consider the second element, deleting the corresponding row and column, we get 0. Then we have 0, deleting this row and column, we get 2, but we need to consider the sign, and this element has position 2, 1. So 1 plus 2 is equal to 3, minus 1 to the power of 3 is minus 1, so we get minus 2. And finally, we need to consider this element, which is 1, deleting the row and the column, we get this element, which is 1. The sign is positive because minus 1 to the power of 2 plus 2 is 1, so we get 1. This is the matrix of cofactor. Now we need to consider the adjoint matrix, which is the matrix, the transpose or matrix of cofactor. So it will be equal to the first row becomes first column, and the second row becomes second columns. And this is the so-called adjoint matrix. In order to determine the inverse of matrix A, we need to compute the determinant of A. We can apply the rule, so we have 1 times 1 minus 0 times 2, which is equal to 1. So if we want to compute the inverse of matrix A, this is equal to 1 over the determinant of matrix A times the adjoint matrix. So in this case will be equal to the adjoint matrix. So this is also the inverse of matrix A. Now we can check that the inverse we have found is correct. We know that if we multiply matrix A by the inverse, this will be equal to the inverse of matrix A times A, and will be equal to the identity matrix. And we can check now. In particular, A times the inverse of matrix A will be equal to the original matrix, which was 1 minus 2, 0, 1, multiplied by the inverse. The inverse is equal to 1 minus 2, 0, 1. We can try to compute this product. So we can repeat the rule to consider the product. This is conformable for product, and we can try the first row and the first column. So we have 1 times 1 plus minus 2 times 0, which is equal to 1. Then we consider first row and second column. So 1 times minus 2 is equal to minus 2, plus minus 2 times 1, which is equal to 2, and we get 0. Then we consider second row and first column. So we have 0 times 1 plus 1 times 0, which is equal to 0. Then we consider second column and second row. So we have 0 times minus 2, which is equal to 0, plus 1 times 1, which is equal to 1. And we get this matrix, which is the so-called identity matrix. Again, you can try it by yourself to compute A minus 1 times A. I remember that when we multiply matrix A times matrix B, is not the same to compute the matrix B times matrix A. In this case, we can compute also A to inverse of matrix A times matrix A. You can try by yourself and check in the lecture later. Okay, we can try. So the inverse is 1 minus 2, 0, 1. We can multiply by the matrix A, I minus 2, 0, 1, and we get first row, first column, 1 times 1 minus 2 times 0, which is equal to 1. First row, second columns, we get 1 times minus 2 plus minus 2. Sorry, this is not minus 2. In the original matrix, matrix A is plus 2. So also here this is plus 2 in order to get the identity matrix. You can check by yourself. So we get final results is the identity matrix if you try to multiply these two matrices. So our computational inverse of matrix A is correct.